Mercury stands as our solar system's innermost planet, orbiting closest to the Sun in an elliptical path that reveals unique astronomical phenomena, unparalleled by any other planetary body. Its proximity to our star creates extreme conditions and unusual orbital behaviors that have fascinated astronomers for centuries. The planet's position relative to the Sun dictates its physical characteristics, observational opportunities from Earth, and even its internal evolution. This report provides a detailed examination of Mercury's orbital dynamics, rotational peculiarities, and the complex relationship between its position and the solar influence that dominates this small rocky world. Mercury orbits the Sun at an average distance of 0.387 astronomical units, AU, which translates to approximately 57.9 million kilometers from our star. This proximity makes Mercury the closest planet to the Sun, experiencing the most intense solar radiation of any planet in our solar system. To put this distance in perspective, Mercury is roughly 7 million times the height of Mount Everest from the Sun. The planet's relatively small size, with a diameter of only 4,280 kilometers, about 38.3% of Earth's diameter, contributes to its rapid orbital period. Mercury completes a single orbit around the Sun in just 87.969 Earth days, making it the fastest orbiting planet in our solar system. This swift journey is facilitated by Mercury's high orbital velocity, which averages 47.9 kilometers per second. However, this speed is not constant due to Mercury's notably eccentric orbit. The planet's orbital eccentricity of 0.2056 is significantly higher than Earth's eccentricity of 0.0167, making Mercury's orbit one of the most elliptical among the planets. This eccentricity creates substantial variations in Mercury's orbital velocity and distance from the Sun throughout its orbit. At perihelion, the closest point to the Sun in its orbit, Mercury's orbital velocity reaches a maximum of 58.97 kilometers per second. In contrast, at aphelion, the farthest point from the Sun, Mercury's orbital velocity decreases to a minimum of 38.86 kilometers per second. This significant variation in speed, more than 20 kilometers per second, demonstrates the strong influence of the Sun's gravitational pull on Mercury at different points in its orbit. The actual distance between Mercury and the Sun ranges considerably throughout its orbital path due to this eccentricity. Another distinctive feature of Mercury's orbit is its inclination. Mercury's orbital plane is tilted at an angle of 7.4 degrees relative to Earth's orbital plane, the ecliptic. This represents the largest inclination among the 8 major planets in our solar system. This orbital inclination has important implications for observing Mercury from Earth, particularly regarding phenomena such as transits, which can only occur during specific alignments when Mercury crosses the plane of the ecliptic. Mercury's rotation presents one of the most fascinating aspects of its relationship with the Sun. For many years, astronomers believed that Mercury was tidally locked to the Sun in synchronous rotation, similar to how the Moon always presents the same face to Earth. This would have meant that one side of Mercury perpetually faced the Sun while the other remained in darkness. However, radar observations in 1965 definitively disproved this theory, revealing a more complex rotational pattern. Mercury actually exhibits a 3.2 spin-orbit resonance, meaning it rotates exactly 3 times on its axis for every 2 orbits it completes around the Sun. This results in a sidereal rotation period, the time taken to complete one full rotation relative to the distant stars, of 58.646 Earth days. However, due to this resonance, a solar day on Mercury, the time between one noon and the next, lasts approximately 176 Earth days, which is twice as long as a Mercurian year. This creates a remarkably extended day-night cycle on the planet's surface. The stability of this 3.2 resonance is directly related to Mercury's eccentric orbit. At perihelion, when Mercury is closest to the Sun, the solar tide exerts its strongest influence, and the Sun appears nearly stationary in Mercury's sky. This tidal force acts on a permanent dipole component of Mercury's mass distribution, specifically aligning the planet's axis of least inertia to point roughly toward the Sun during perihelion passages. In a perfectly circular orbit, such variance would not exist, and the only stable resonance would be a 1.1 ratio, synchronous rotation. Recent simulation studies have demonstrated that Mercury was captured into this 3.2 spin orbit state very early in its history, likely within the first 20 million years after its formation, and possibly as early as 10 million years post-formation. This contradicts earlier theories that suggested the resonance arose during periods of high orbital eccentricity over the course of millions of years of evolution. The early capture into this resonance has had profound implications for the thermal evolution and surface conditions on Mercury. The appearance and behavior of the Sun in Mercury's sky create some of the most unusual astronomical phenomena in our solar system. Due to Mercury's proximity to the Sun, the star appears significantly larger in Mercury's sky than it does from Earth. The angular size of the Sun as seen from Mercury ranges from 1/14 to 2 degrees across. By comparison, the Sun appears only about 1/2 degree across when viewed from Earth, making the Sun appear 2.5 to 4 times larger in Mercury's sky. Mercury's nearly zero axial tilt, approximately 0.027 degrees compared to Earth's 23.5 degrees, means there are no seasonal variations in solar illumination. This extremely small tilt has interesting consequences for observers at Mercury's poles, where the center of the Sun never rises more than 2.1 arc minutes above the horizon. This creates permanent shadows in deep polar craters, which has allowed water ice to exist in these permanently shadowed regions, despite the otherwise scorching surface temperatures. One of the most remarkable phenomena occurring on Mercury is the apparent retrograde motion of the Sun in Mercury's sky at certain locations and times. Approximately 4 Earth days before perihelion, Mercury's angular orbital velocity equals its angular rotational velocity, causing the Sun's apparent motion across Mercury's sky to momentarily stop. As Mercury moves closer to perihelion, its orbital angular velocity exceeds its rotational angular velocity, causing the Sun to appear to move backward in a retrograde direction in Mercury's sky. 4 Earth days after perihelion, the Sun's normal apparent motion resumes as Mercury's orbital velocity decreases. This unusual solar motion creates extraordinary viewing conditions at specific points on Mercury's equator. There are 2 points on Mercury's equator, 180 degrees apart in longitude, where during alternate Mercurian years, once per Mercurian day, the Sun passes overhead, then reverses direction and passes overhead again, and then reverses a second time to pass overhead a third time. This entire process takes approximately 16 Earth days. In alternate Mercurian years, this same phenomenon occurs at the other equatorial point. The overall effect is that for 2 or 3 weeks at these locations, the Sun appears almost stationary overhead and at its most brilliant, as these events coincide with Mercury's perihelion when it is closest to the Sun. The proximity and orbital relationship of Mercury to the Sun create extreme temperature variations across the planet's surface. The surface temperature on Mercury ranges from 90 to 700 Kelvin, 183 degrees to 427 degrees C, or 297 degrees to 801 degrees. The hottest regions occur where the Sun's rays strike perpendicular to the surface, while the coolest temperatures are found in craters at the poles that never receive direct sunlight. Mercury's solar irradiance, the amount of solar energy received per unit area, is approximately 9,082.7 watts per square meter compared to Earth's 1,361.0 watts per square meter. This means Mercury receives almost 6.7 times more solar energy per unit area than Earth does. This intense solar radiation contributes to Mercury's calculated blackbody temperature of 439.6 Kelvin, significantly higher than Earth's 254.0 Kelvin. The 2 points on Mercury's equator that experience the triple overhead sun passage during perihelion are the hottest places on the planet. Maximum temperature at these locations occurs when the Sun is at an angle of about 25 degrees past noon due to diurnal temperature lag, approximately 0.4 Mercury days and 0.8 Mercury years after sunrise. Conversely, the 2 equatorial points located 90 degrees of longitude away from these hot spots experience overhead sun passages only during aphelion in alternate years, when the sun's apparent motion in Mercury's sky is relatively rapid. These regions receive much less solar heat than the primary hotspots. Mercury's position between Earth and the Sun creates specific observational constraints and opportunities. From Earth's perspective, Mercury never appears more than 28 degrees away from the Sun. This maximum angular separation is known as the greatest elongation and varies between 17.9 degrees at perihelion to 27.8 degrees at aphelion. This limited elongation means Mercury is always relatively close to the Sun in our sky, making it challenging to observe against the bright background twilight. Mercury attains an inferior conjunction, its closest approach to Earth when it passes between Earth and the Sun, every 116 Earth days on average. However, due to Mercury's eccentric orbit, this interval can range from 105 to 129 days. During these approaches, Mercury can come as near as 82.2 million kilometers to Earth. Historical data indicates this minimum distance is slowly declining. The next approach to within 82.1 million kilometers will occur in 2679, and to within 82.0 million kilometers in 4487. However, Mercury will not come closer than 80.0 million kilometers to Earth until the year 28,622. When viewed from Earth, Mercury exhibits retrograde motion for varying periods around inferior conjunction. This retrograde period can range from 8 to 15 days on either side of the inferior conjunction, with the wide range resulting from Mercury's high orbital eccentricity. Interestingly, when averaged over time, Mercury is often the closest planet to Earth, and by extension, the closest planet to each of the other planets in the solar system. This counterintuitive fact results from Mercury's position as the innermost planet. Mercury is best observed at first and last quarter phases, despite these being phases of lesser brightness. These quarter phases coincide with greatest eastern elongation, when Mercury sets at its latest after sunset, and greatest western elongation, when Mercury rises at its earliest before sunrise. Mercury is generally more visible from the southern hemisphere than from the northern hemisphere. This hemispheric advantage occurs because Mercury's maximum western elongation coincides with early autumn in the southern hemisphere, while its greatest eastern elongation happens during late winter in the southern hemisphere. During these seasons, the angle at which Mercury's orbit intersects the horizon is maximized, allowing it to rise several hours before sunrise, or set several hours after sunset when viewed from southern mid-latitudes. One of the most significant observational phenomena related to Mercury's position is a transit, which occurs when Mercury passes directly between Earth and the Sun, appearing as a small black dot moving across the solar disk. Due to Mercury's 7-degree orbital inclination relative to Earth's orbital plane, transits can only occur when Mercury is crossing the plane of the ecliptic at the time it lies between Earth and the Sun. This specific alignment limits transits to May or November, occurring approximately every 7 years on average. During a transit, observers on Earth can directly witness Mercury's position relative to the Sun with appropriate solar viewing equipment. The planet appears as a perfectly circular black dot against the bright solar surface, with an apparent diameter of only about 10 arcseconds, compared to the Sun's approximate 1/800 arcseconds. This tiny size means Mercury occupies only about 1/30,000th of the Sun's visible area during a transit, making it impossible to observe without magnification and proper solar filters. The precise timing and duration of Mercury transits vary due to the eccentricity of Mercury's orbit and the relative positions of Earth and Mercury in their respective orbits. Mercury transits provide valuable opportunities for astronomers to refine orbital calculations and study the planet's atmosphere through observations of sunlight filtering around Mercury's limb during ingress and egress phases of the transit. Mercury's position relative to the Sun is not static over long timescales. Numerical simulations indicate that Mercury's orbital eccentricity varies chaotically from nearly zero, almost circular, to more than 0.45 over millions of years, due to gravitational perturbations from the other planets. These variations have implications for Mercury's spin-orbit resonance and its thermal environment. More concerning from a long-term perspective is the potential for orbital instability. Accurate models suggest that a future secular orbital resonant interaction between Mercury's orbit and the perihelion of Jupiter may cause Mercury's orbital eccentricity to increase dramatically. This increasing eccentricity could eventually lead to significant orbital instability, with simulations suggesting there is approximately a 1% chance that Mercury's orbit could be destabilized within the next 5 billion years. If such destabilization occurs, Mercury might fall into the Sun, collide with Venus, be ejected from the solar system entirely, or even disrupt the orbits of other inner planets. Mercury's longitude system is directly related to its position relative to the Sun. The longitude convention for Mercury places the zero of longitude at one of the two hottest points on the surface, where the Sun appears to pass overhead 3 times during a single Mercury day near perihelion. However, when the Mariner 10 mission first visited Mercury, this zero meridian was in darkness, making it impossible to select a specific surface feature to define the exact position of the meridian. Instead, scientists chose a small crater farther west named Huncal to provide the exact reference point for measuring longitude. The center of Huncal defines the 20th west meridian. A 1970 International Astronomical Union resolution suggested that longitudes on Mercury be measured positively in the westerly direction. Following this convention, the two hottest places on the equator are at longitudes 0° west and 180° west, while the coolest points on the equator are at longitudes 90° west and 270° west. However, it's worth noting that the Messenger mission, which orbited Mercury from 2011 to 2015, used an east-positive convention for its mapping and scientific studies. Our understanding of Mercury's position relative to the Sun has evolved significantly through spacecraft exploration. The first dedicated mission to Mercury was Mariner 10, which conducted flyby observations from 1974 to 1975, mapping approximately 45% of Mercury's surface. The Messenger mission conducted 2 flybys in 2008 and 2009, mapping an additional 30% of the surface, before entering orbit around Mercury from 2011 to 2015. These missions provided critical data about Mercury's orbital parameters, rotation, and surface features that have refined our understanding of its position relative to the Sun. Before these spacecraft visits, ground-based observations provided limited information about Mercury. The planet's proximity to the Sun made it challenging to observe with telescopes, and its small size presented difficulties in resolving surface features from Earth. Early astronomers, including Johannes Kepler, used observations of Mercury's position to help develop the laws of planetary motion that described how planets orbit the Sun in elliptical paths. These observations were crucial in the shift from geocentric to heliocentric models of the solar system. An alternative method for viewing Mercury involves observing the planet with a telescope during daylight hours when conditions are clear, ideally at its greatest elongation. This technique allows astronomers to find Mercury more easily, even with modest telescopes having apertures as small as 8 centimeters. However, extreme caution must be taken to prevent direct viewing of the Sun, which can cause severe eye damage. This method circumvents the limitations of twilight observing when the ecliptic is low on the horizon, allowing observations when Mercury is higher in the sky and less affected by atmospheric distortion. Mercury's position as the innermost planet in our solar system creates a unique relationship with the Sun that influences every aspect of the planet's physical characteristics and behavior. From its rapid 88-day orbit and eccentric path to its 3.2 spin-orbit resonance and extreme temperature variations, Mercury exemplifies the profound influence of solar proximity on a planetary body. The peculiar phenomena observed on Mercury, including the triple sunrise and sunset effect, the apparent retrograde motion of the Sun in Mercury's sky, and the extreme thermal gradients, all stem directly from its position relative to our star. The challenges in observing Mercury from Earth reflect its close solar proximity, with the planet never straying far from the Sun in our sky. This positioning also creates the relatively rare but scientifically valuable transits across the solar disk, allowing direct observation of Mercury silhouetted against the Sun. Long-term orbital dynamics suggest Mercury's relationship with the Sun may not be permanently stable, with a small but significant chance of major orbital changes in the distant future. As our closest planetary neighbor to the Sun, Mercury serves as an important case study in understanding the effects of intense solar radiation, gravitational interactions, and tidal forces on planetary evolution. Its unique position has shaped its physical properties, orbital characteristics, and rotational behavior in ways that continue to fascinate astronomers and planetary scientists. Through continued observation and future missions, our understanding of Mercury's relationship with the Sun will undoubtedly continue to evolve, providing new insights into the dynamics of our inner solar system.